Hello, and welcome to the lecture video accompanying Chapter 19 on the topic of celestial distances from OpenStax astronomy. All right, so let's get into discussing how astronomers know how far away stars are. Okay, this is a topic, an idea, a mystery even, that I've hinted at in previous chapters and we want to finally introduce. And I'll start with a caveat to say that we're not going to completely cover cosmic distances. In fact, the title or the idea of stellar distances is very accurate. We're going to focus on the distances to stars, and we'll leave the mystery of galactic distances for another chapter. Okay? And by the way, here we're looking at a cluster of stars. It's called the Globular Cluster M80. That's its modern name. And the reason that this is the introductory image for the chapter is this particular cluster historically for astronomers was a key location in the sky, a key population of stars that was studied in order to reveal the secrets of something called variable stars. And if you look right there, that word shows up in the description. So that's one of the key ideas we're going to come back to. But first, let's establish a little bit more background. Okay, so distances in general start in the early 1800s with observing the transit of Venus across the sun. Okay, so here we have a point a few hundred years after firmly establishing that the sun was the center of the solar system, further beginning to understand the idea of other distant stars, the concept of a galaxy, but all these were still very rudimentary in the early 1800s. But one thing that started to pave the way for further progress in our understanding of the vast distances between objects out there in space was observing our nearest by planet, Venus. Okay, our nearest neighbor. Because when Venus crossed in front of the sun, a more common event, by the way, than Mercury transiting in front of the sun, we were able to measure the time it took for Venus to cross the sun. And by doing that at multiple locations on Earth, use a process known as triangulation, which I'll mention again in a couple of slides, to essentially measure the distance to Venus. It all has to do with angles, and in this case we had the advantage since the Venus was moving, we were able to measure the speed at different points, which gave us a really accurate measurement. So in other words, the transit of Venus across the sun allowed us to measure the distance to Venus. Okay? We started to get an idea of how far away planets were. Of course, this then led to the idea of an astronomical unit. Okay? A quantity that we have seen before. A quantity that is equal to, as a good reminder here, 1.50 times 10 to the 11 meters. Okay? Or in other words, 150 million kilometers, okay? Which is also 500 light seconds. All right, now Venus is not 1 AU away, but the sun is 1 AU away from us, okay? All right, so early established distances. Now, it turns out that this idea of having accurate distances for planets and for the AU, again, the average distance of Earth from the sun, is so important for everything else we're going to talk about. And the most accurate way to measure distances to Venus, distances to Mercury, distances to Jupiter, or even distances to the sun's surface itself is to bounce radio waves off of those other objects. And this is an example of a radar telescope that is used to send a very concentrated radio wave, like radio waves that are used for FM and AM radio, send it out into space, so right through Earth's atmosphere, bounce it off of a planet, or a moon, or a comet, or an asteroid, and then detect the faint signal that returns to Earth, hence the huge dish here. It is a totally doable process. Obviously, we need the right kind of filters, we need the right kind of circuitry, we need a very sophisticated large device, but we can get very accurate readings of how much time it takes for that radio wave to go, hit something, and then travel back, all right, and thus be detected. And if we know the total time it took the radio wave to go, bounce off the sun, for example, and then come back, we now have a measurement of distance. Why is that? Because radio waves travel at the speed of light, okay? Because radio waves are a form of light, okay? So they travel at c, which is 3.00 times 10 to the 8 meters per second. They travel at 300 million meters per second. Just like visible light, like red, green, blue, violet, indigo, visible light, right? Just like X-rays, all forms of light travel at that same speed, okay? At least in the vacuum of space, and that's what we're concerned about here. All right, so now we can get really accurate measurements, right? We can just bounce radio waves. We could even bounce them off the distant planets in our solar system. We could even bounce a radio wave off Pluto if we're really accurate in aiming, okay? But most importantly, really, is bouncing that radio wave off of the sun and getting a really, really good measurement of what? Of Earth's orbital radius, okay? Because if you recall, there was this idea of parallax, okay? But now I'm going to get into parallax, but I want to mention this slide. These are the order that the figures are in your book. And this is just establishing the idea of triangulation. So essentially we can measure two, in this case, so measure two distances allows us to measure a distance to an inaccessible object by getting the angle to a tree from two different vantage points. All right? So if we measure this angle and then this angle, and then we know how far apart our two measurements are, then we can calculate this dotted line as well as any other lines. Okay, we can get the distance to the tree. So again, we need a baseline, and we need we'll have these be our angles. Okay, we'll have this angle. Okay, so that's it. As long as we have an angle, really just one angle and a baseline, then we can measure a distance. It's basically trigonometry, like right triangle trigonometry. Okay, because essentially we've taken this non-right triangle, sort of essentially an isosceles triangle, and this dotted line down the middle has turned into two right triangles that we can then use to make our calculation. All right, that's the basic principle of triangulation. That's what would have been used for the transit of Venus to measure the distance of Venus, okay? And now, do we need triangulation for radio waves? Not at all. This is a totally different technique, more modern. So it might seem like I'm kind of bouncing back and forth a little bit. I'm saying, okay, well, we used triangulation for Venus way back in the early 1800s. These days, we would just use a radio wave to measure the distance of Venus or the distance of the sun. But yet, here's triangulation again. That's because triangulation actually has a big role to play in something that we cannot bounce a radio wave off of, and that is other stars. So let's think about that, right? We can send a radio wave out into space and we can bounce off a planet because it only takes a few minutes for light to travel from Earth to other planets. It does take minutes, it's not instantaneous. Even hours if we're bouncing off distant planets. But it's doable, right? We can wait for that signal to come back. If I was, on the other hand, if an astronomer rather, a scientist, was to aim the most powerful radio dish at our closest neighboring star and send a radio wave exactly aimed at that star, and then wait for that radio wave to come back to us, it would take over 9 years for that to happen, okay? Because it would be about 4.5 light years to get there, and that means the light would take 4.5 years, because the light year is a distance, but it's also how long it takes light to travel that distance. So it would take about 4.5 years for the radio wave to get to that closest star, and then 4.5 years for the reflection to get back to us. So 9 years, okay, well, I mean, scientists do studies that take 9 years, but we'd have to accurately aim that radio wave at something that it takes up so little actual angular space in the aiming process of that telescope. Furthermore, when the wave came back to us, it would be so diffuse because that energy would be spread out over such a great distance And no matter how concentrated the initial wave was, the reflected wave would be almost imperceptible to measure, right? Could we possibly measure it? Yeah. Is this a possible measurement, a possible experiment that could be done? Yes. All right. But I don't know if it ever has, and I don't know if it ever will, because there's so many. There would be such technical hurdles to get there, and there is another way of measuring the distance to that nearest star, as well as other stars that maybe might be 10, 60 light years, 150 light years, in which case the total travel time being 300 would be unreasonable. We're not going to set up a multi-generational process to just wait for a signal to bounce back. Okay? So, how are we going to measure the distance to stars, even the closest ones? We're going to use stellar parallax. And the first person that was successfully able to measure stellar parallax was the German scientist Friedrich Bessel, all right? And then shortly after that, we had Scottish scientist Thomas Henderson and Russian scientist Friedrich Struve, okay? So, there you go. People started to measure stellar parallax. And I make a big deal about that because remember, stellar parallax was the idea that made great minds of the ancient era, I think the Greeks, reject the notion that the sun was the center of the solar system, because if Earth was in fact orbiting, taking this huge path around this distant, ball of fire called the sun, then the stars would have to move in the sky, right? Because if we're moving through space, the stars must be moving. It's like triangulation. If I move my detection device a certain baseline, in this case, the baseline would be the diameter of Earth's orbit, right? So if I'm moving my baseline, then my angle to some object, the tree, has to change, right? It absolutely has to change, okay? But what if that tree is much further away, right? What if it's like way on the other side of the mountains? We still have a clear view of it, right? Because the stars, we can see them. There's nothing obstructing them. So, it's just a very, very long valley. But if that's the case, right? If the tree is that much further away, then how do we measure it, right? In fact, the idea is that these changes, the angles that these early astronomers and scientists were measuring, were like measuring the size of a quarter that was 5 kilometers away. So think that's about 3 miles. So think a quarter 3 miles away, and then trying to get a high-powered scope to actually measure the diameter of that quarter 3 miles away, right? At 3 miles, it is almost impossible to get a good enough telescope to see something as small as a quarter. Okay? Now it is possible, and it turned out that it was that certainly it wouldn't have been in the 1500s or the 1600s, but by the time we get into the early 19th century, our telescopes are good enough that we are able to measure that type of small object or small angular displacement. Okay? But in this case, we're not measuring a quarter. We're not measuring a single object that's that big. So I'm not saying the stars have an angular size that is that large. But instead, we're measuring their motion. Here's the idea, all right? If we take a measurement at point A and we observe that the star, the red one here, is located there relative to stars that are even further away, and then we take a measurement at point B and observe that the nearby star, because this method we're going to see only works for relatively nearby stars, depending on how accurately it's done, that red nearby star has moved. The distance it's moved is about that far, drawn on both ones, right? So that right there is the angular change. That's the parallax, okay? The little red arrow I made is the parallax, okay? That's the shift of the object relative to things behind it, to more distant objects behind it, in this case, more distant stars behind the nearby star. And the parallax is due to the fact that we have a baseline. So parallax and triangulation are the same idea, right? They're just kind of two words for the same idea. One is the method, one is the observation or the phenomenon. Okay, so that smallest parallax, or actually the largest parallax, the biggest case that we're going to see is for the closest stars. So the closest stars are the ones that are going to shift the most. And it was the closest stars that these scientists were observing. Okay? And when they observed that shift, they ended up finding a shift, a maximum parallax angle of about 1.5 arc seconds. Okay? So max parallax is 1.5 arc seconds. Okay? That's the maximum angular shift. All right? That would be this angle right here. 1.5 degrees. Well, excuse me, not degrees. 1.5 arc seconds. I said degrees, so I was thinking an angle. But of course, an arc second is a fraction of a degree. And as a quick reminder, 1 degree is 60 minutes, and 1 arc minute is 60 arc seconds, which means that 1 degree is 3,600, which is 60 times 60 arc seconds. Okay, so it's 3,600 arc seconds per degree, and the degree isn't that big to begin with. Okay, I mean it's fairly large angular coverage on the sky, but you take less than a 3,000th of that. That's a tiny, tiny shift. You definitely cannot observe arc second motion or arc second size objects in the sky with the naked eye. Okay, that type of size is too small. Now the stars themselves have smaller diameters than that, but their light is diffuse, right? We still see the bright light, but you can think of every single star other than our sun as being a single point. It has, to the naked eye, it has no measurable diameter. Okay? I know I had a homework problem where I talked about the measurable diameter of a star, but that's using the most powerful telescopes, not the human eye. All right, just kind of quick reality check there about that the stars are effectively pointed, single points. Okay? But the motion isn't. Okay? The motion of nearby stars is measurable with just a decent telescope, nothing special. Pair of binoculars, you could see arc second movement if you're really carefully mapping it. But you have to be patient because you're not going to see this 1.5 arc seconds of movement until a full 6 months later, right? Because that's half a year. Okay, so that's the idea. We actually are now we're at a point in astronomy, in the history of astronomy, okay, where we're actually measuring stellar parallax. And that's a huge deal because already, in the early 1900s, we had, early 19th century, early 1800s, we had an idea about distances like the distance to Venus and so on. Certainly today, we have a very good measurement of Earth's orbital diameter, okay, our d. So that means that once we have a measured angular parallax, we really know how far away those stars are, okay? This is the big breakthrough. We actually know how far stars are from us, okay? Now that we know that, now we can really start naming stars because now we have them, we can measure their distances, we can measure their luminosity, we can measure, and that's, before we could only measure their apparent brightness. Now we can actually take that apparent brightness and calculate luminosity. We can take measurement, we can measure their temperature already based on their spectrum. We can kind of group them together, think the HR diagram, which I'll mention again in a few slides. And so the purpose of this slide in figure 19.7 is to point out that now we're really at a point where we can be confident about stars and really start classifying them in every way. Okay? Really start naming stars. Furthermore, this establishment of parallax is going to give us a new kind of really common unit of distance. And that is the unit of the parsec. Okay? So I'll write it on this figure and then I'll talk about kind of what this figure represents. But I want to mention this new unit for us. So new unit of distance that is with its importance coming to the forefront due to the ability of measuring stellar distances with parallax, okay? And that distance is the parsec, okay? Now a parsec represents a star that has 1 arcsecond of angular parallax. Okay, that's what the parsec is. It's exactly 1 arcsecond of angular parallax. All right. So 1 arcsecond of angular parallax. All right. Now that's its definition, but that's not going to allow us to convert to other distances, because after all, I say it's a distance, right? So what is it say in other units of distance? Well, a parsec is equal to 3.1 times 10 to the 13 kilometers. Okay, and that is equivalent to 3.26 light years. Okay, so first of all, that's a huge distance, because the light year already was a mind-bogglingly large distance, and so that's telling us that a parsec is bigger than light years. It's over 3 light years. And that's because the very closest stars, the reason we're even using this unit, that this unit has gained popularity and is used, is because the closest stars are about 1 parsec in angular shift, in terms of angular parallax. All right, and in fact, I mean, hundreds of years ago, a couple hundred years ago, they kind of rounded to exactly 1 parsec as the distance to those nearest stars. We know now that the nearest stars, Alpha Centauri A, Alpha Centauri B, Alpha Proxima, the 3 closest stars to Earth, they're actually about a 1.5 parsecs away. All right, so the one was a little bit too generous. Okay, the stars are significantly further than that, like half again as far away. But regardless, that 1 parsec stuck around, and it does, and also it stuck around because it's exactly 1 arcsecond. And I guess it was just too convenient to have any stars that were exactly 1 arcsecond of parallax away. All right, so the closest are about 1.5 arcseconds of parallax, thus 1.5 parsecs. Thus 3.26 times 1.5, okay? And I bring this up because definitely this is going to be a homework question, just a straightforward conversion question. I want you to get used to this new unit. I'm not sure what the second one will be. I'll be posting the homework shortly after recording this video, so maybe you've already seen it. But regardless, at least one of them will be a conversion problem like this, okay? But I did mention why I would, or how I would tie together this introduction to this new unit to this graph we're looking at here with a horizontal axis of luminosity and a vertical axis of luminosity and a horizontal axis of spectral type. And obviously this is an HR diagram, right? But what's special about this HR diagram is all the stars shown on it represent stars that we have measured with stellar parallax. So these are all stars that we know their spectral type, in other words, we know their temperature, and we know their true luminosity because we know how far away they are, okay? These are stars that we're very confident about, because we measure their apparent brightness. Okay, maybe we measure it as apparent magnitude and use the relationship between apparent magnitude and apparent brightness. But regardless, we take that and then we use that with distance to calculate true luminosity, absolute luminosity. All right, and that will probably be the other calculation that you're going to be doing this week, is the calculation between distance, brightness, and luminosity. And it just has to do with the idea that as energy spreads out, it falls off as the square of distance. Okay, it's an inverse square relationship, but I'll give you the formula and I'll explain some background of it. Not here in the slides because the book doesn't get into it, but it'll be a good kind of follow-up. The end of the chapter questions do, but the main body of the text does not. Okay, but regardless, this is it. These are stars we really know. We really know their luminosities, right? Now, it was calculated, but it was calculated from 2 very accurate measurements, brightness and distance. And distance was found with parallax. Okay, you get that? See how it's tying together? Okay, so there's one more piece of the puzzle here, all right? Now really there's another one, and there's a couple more, but we're going to save them for another chapter. But there's one more distance idea, stellar distance idea that we're going to introduce before we wrap up this lecture and wrap up this video. And that's the idea of cepheid variables. And we'll mention one other type of variable star as well. What's a cepheid? That's a weird word, right? Well, cepheid, the name just comes from the name of the constellation where they're first discovered. All right, so it's kind of a historic name. It doesn't mean anything. It's just again named after the variable. Cepheid is probably a Greek god or something. So, but name notwithstanding, what it is it's a variable star. Notice the graph here. Vertical axis, magnitude. That's just brightness, right? Not even saying luminosity. This is just measured brightness. Okay, this is where we got a telescope. We're just looking at a star. We don't know anything about it, except we notice that its brightness is measured on Earth varies over time with a variation that takes a couple days, right? It's not rapid. It's not like, minutes or anything. But every few days, the star gets noticeably less bright and noticeably more bright in this nice rhythmic fashion. Bright, less bright, bright, less bright. Okay? So what's going on? Why are these stars doing it? Well, it turns out they're going through this unstable phase in their lifespan as a star, where this idea about the fusion core is kind of unstable, causing the star's surface to get bigger and smaller. So the star is actually physically pulsating in size, and as it pulsates in size, we know there's a direct relationship between area, surface area, and luminosity. Thus, there must be a relationship between luminosity and apparent brightness measured here on Earth, and apparent magnitude for that matter. Okay? So that's kind of the physical process. We won't get into that because we haven't talked about fusion or types of stars or the life cycle of stars, right? And because this is kind of one particular stage in the life cycle of certain types of stars. Okay, but the important thing is it's fairly common. There are a lot of stars that do this, that we see doing it, and they may not do it their whole life, right? They may only do it for 100 million years and stop. But we look into the sky and we find a lot of stars that do this. They fluctuate, okay? And it's not most of the stars. It's just a small fraction of the population of the total stars that do it, right? Like, let's say less than 1% of total stars actually fluctuate like this, but that's still a lot of stars. Okay, so here's a big historical figure that made some breakthroughs with cepheid variables. So Leavitt worked as an astronomer at the Harvard College Observatory. I'm just going to read this to give you the background. While studying photographs of the Magellanic Clouds, that was that introductory photo for the set of slides here, she found over 1,700 variable stars, including 20 cepheids. Okay, just that one type of variable star. Since all the cepheids in the system were roughly at the same distance, she was able to compare their luminosities and periods of variation. She thus discovered a fundamental relationship between these characteristics. So think about that. She knew they were all the same distance because there's these certain clouds and they were clearly, all the stars were formed. So we're not just looking at an overlay of distant stars and closer stars. When we find these particular clouds that were birthing grounds for stars, we actually know all those stars are about the same distance from Earth. So right there, that's a great place to start, right? And she didn't necessarily know how far the Magellanic Cloud was away, because perhaps none of these stars were close enough to do stellar parallax. Because, by the way, there are limitations to how far we can do stellar parallax. Just to bring it back to that real fast. We can do, modern astronomy can do stellar parallax up to about a third of the galactic disk, so about 30,000 light years. We can actually measure the tiny, millionth of an arc second variation in stars at that distance. But in the past, certainly in the early 20th century, that distance was limited to about 300 light years. Okay, that's also a testament in the last century we've gone from using stellar parallax on up to a limit of 300 light years now to 30,000 light years. Right, we've gone 2 orders of magnitude greater in our distance of stellar parallax. But ultimately, at some point, we can't go further. There is really a limit, and certainly the edge of the galaxy would be the ultimate limit of where we could use stellar parallax. So then my point is that this Magellanic Cloud might have not been well known in terms of its distance. But what she did, what Henrietta Leavitt did, was saw a relationship, and then was able to leverage that relationship, to use that physical relationship between luminosity and variability, time, period of variation, to say, okay, well, that means if we look at any place in the sky and we find another cepheid variable that is varying its brightness at this rate, we know its true luminosity. So now, instead of, say, confirming that with parallax, we use now the period of the variable star as the distance, okay? Or more like we use it as the true luminosity and then can measure the distance from there. All right? So this is the Large Magellanic Cloud again. So the idea is like this. I will summarize it better through these steps. Okay? Find a cepheid variable star and measure its period. Okay, that's the first thing you would do. Okay? Then use the period luminosity relationship to calculate the star's luminosity. And again, the only other way, other than Cepheid variables, to calculate luminosity would be with parallax and distance. So measure the parallax, measure the distance, measure the brightness, then you know the luminosity. But here, we're skipping all those steps, and we're going straight from period to luminosity. And that's just because of that data that Henrietta collected. That data that said that there's a direct relationship between two things that we didn't realize there was a direct relationship between. True luminosity, the actual power output of the star, and its period of fluctuation when it's going through this particular life stage. And is it just a particular type of star that goes to that particular life stage? But regardless, that's it. Now we actually know it's true luminosity. So now look at step 3. Measure the star's apparent brightness. Okay? Right? That would have been one of the steps for measuring its distance if we were using parallax. And now look. Now that we know true luminosity and apparent brightness, we can calculate distance. All right? So it's another way to calculate distance other than using stellar parallax. It's another tool in our tool belt. And it's not limited to the really careful measurements of angular shift. We can just, because it's based on something that transmits much, much better over much longer distances. And that's just variations in brightness. We can measure that so much more accurately than a tiny angular shift. The stars can be 100,000 light years away, or even in other galaxies. We can actually find Cepheid variables in other galaxies and measure their variation, and thus find the distance to kind of the average point in that whole galaxy. That we could never do with stellar parallax. Okay? So the Cepheid variables both supported stellar parallax, as we were able to confirm that they agreed on the stars that fell, that a Cepheid variable that was in that limit of stellar parallax, say like 500 light years away, there's plenty of Cepheid variables. And so we found agreement between the methods, right? And it also opened up new distances, greater distances that could be accurately measured, okay? And it's not perfect, right? Because what if you need to find a star that's, say, greater than the stellar parallax upper limit of 30,000 light years, but isn't near any Cepheid variables? Well, are you just kind of out of luck? You know, maybe you can find a Cepheid variable that's sort of nearby. You know, so because again, the Cepheid variables will only tell the distance of themselves. So if they're part of a cloud of other stars, that's great, because then you kind of know the distance to all the other stars in that cloud. But what if you find some star that isn't near a Cepheid variable, that isn't part of a cloud at all? Right? So how do you measure its distance? Well, it turns out that what's kind of happened, I'm going to skip over this one. What's kind of happened is that we're able to now find more rules, kind of just build on the data, get more robust data. And it's messy sometimes. It's not perfect, right? But the more data, the better relationships, the better estimates. And then you question the quality of your estimate, and then you make another measurement, and you try to do the best you can as a scientist, right? And by the way, this is the luminosity versus period. This is the trend that was found by Henrietta Leavitt and and her colleagues and scientists that came later. And here's the group of the Cepheids. Here's the other type of variable stars, right? That also have, they're a little bit messier though, these RR Lyra stars, again just named after the constellation where they're first found, because they're all just kind of clustered around one particular luminosity, so there's not like a nice trend. Here there's clearly a slope, right? There's not really a slope for the Lyra stars, there's kind of this one data point. But regardless, this is the idea between period in days of variation and luminosity, the one that was mentioned before, all right? This would be the step B, use the period luminosity relationship. Here it is. And real fast, just so you wonder what this slide is about, this is an astronomer that historically was involved with the early discovery of Cepheid variables. And the interesting part of this was that he was deaf and unable to speak, so deaf and mute, and but still was able to contribute so much to astronomy. So just a testament to these people that are alter abled but still able to make breakthroughs and be productive scientists and so on. So my last point here, to finally wrap this up, is that now with this vast body of knowledge about stars, really understanding the HR diagram, we can now look at a star and not have it necessarily within the parallax limit, not have it necessarily near Cepheid variables that will confirm its distance, but able to look at its spectral type and then observe properties about its density, its maybe particular elements that exist near its surface, and in doing so, split it into one of a few key categories. And those categories are, okay, let me summarize them. I just want to find my list here. Okay. So 1A are the brightest supergiants. 1B are the less luminous supergiants. So 1A and B are both supergiants. And the notation here we're using for 1 is a Roman numeral, and then we're using Arabic letters for A and B. Okay. Well, no, it would be Arabic numerals. I was thinking, so we're using Roman numerals and Roman letters and no Arabic numerals. Okay. So anyway, kind of weird notation note there. And then number 2 is bright giants. That's class 2. Okay. And these are usually called classes of stars. All right. These are luminosity classes. And I'll again wrap it up by just stressing the importance of the classes and why it lets us classify stars that aren't near within the parallax limit or near cepheids. And then we got number 3, which are just giants. Okay. So we've gone from supergiants to bright giants, just plain old giants. And then finally we have class 4, which are subgiants. And at the very end, we got class 5, which is the big main sweep here, which are called main sequence stars. All right. And we'll learn later that it turns out that all the giants, whether they're supergiants, bright supergiants, or whatever, are all dying stars. But the important thing is that we need these classes because otherwise, if we have a star that isn't near a cepheid and isn't within the parallax limit, and we just measure its surface temperature, then we have kind of a vertical line of information. But we don't know if it's a supergiant, a brightest supergiant, a supergiant, and so on. But now that we know, so we've learned by finding stars that are close by and able to confirm with independent results, we've learned so much about the luminosity of these other types of stars, tied in with other characteristics about their spectrum, the little details of their spectrum, the little things that are missing in terms of the elements, in terms of the absorption patterns, and so on, that we can actually distinguish between 5 different stars that all would have a surface temperature of 6,000 Kelvin. Okay, but we got there thanks to, well, first of all, transit of Venus, second of all, stellar parallax, and third of all, understanding of cepheid variables. And that's the story that this chapter is telling. Okay, so I think I should wrap it up there. That's a great stopping point. I hope this is all made a little bit of sense, helped to kind of fit ideas together. The one kind of tantalizing bit of information I'll leave you with is we still have another kind of standard for measuring distances called white dwarf supernovas that we'll talk about later. And then finally, the real pinnacle of distances that even all the way back to the Big Bang, which is called Hubble's law. All right, but we're going to save that when we talk about galaxies and things at a greater scale. But hopefully this has really started to or maybe continue to pique your interest. And thank you so much for watching this video.